This video is on the fundamental theorem of calculus, and obviously that's a very important name, so this is something that you really need to pay attention to. So we've talked about how this represents the area from A to B, this integrand, and then A to B of a certain function. We're looking at the area between A and B of that function and the x-axis. And we talked about where all that came from. What we're going to be doing today is actually figuring out how to come up with the answer for that exact area. And the first thing we're going to do is say that we're going to take the antiderivative of f of x, which you're used to doing, and I'm going to call that capital F of x. And then we're going to put a straight line, and we're going to put the a and b here. And what that means is we're going to evaluate that antiderivative for a and b. And our fundamental theorem of calculus rule says that we're going to plug in the top number. So we're going to find out what that antiderivative with b plugged in is, and subtract, and then plug in the bottom number. So again, I have that antiderivative, I'm plugging in that a, whatever that number is. And we should get a numeric answer here, and that would be the exact area that we were trying to find before. And we were unable to do so because we didn't know everything yet. So this is how that works. So let's move on to some examples. Okay, so for our first example, we have the integral from 1 to 2 of x squared minus 3 dx. And the first thing I'm going to do is figure out what my antiderivative is. And so this is just a power rule. And so it comes out to be 1/3 x cubed. And then minus, and 3 gets to get an x with it, so it becomes 3x. And again, I'm going to put that line there and it tells that I'm evaluating from 1 to 2. Now, when you have a situation like this where you have a minus or a plus or different things added or subtracted together, you need to keep that answer together when you plug in the 1 and the 2. And so I tend to put a big parentheses around it. So the first thing I'm going to do is plug in the 2. So 1/3 times 2 cubed minus 3 times 2, and put a big parentheses around that. So that'll be a numeric answer for plugging in 2. Subtract, put a big parentheses, and then plug in the 1. 1/3 times 1 cubed minus 3 times 1. And so it has the answer for 2 subtracting the answer for 1, and I won't mess up my signs that way. And so I know that 2 cubed is 8, so I have 8/3 minus 6, and that ends up to be negative 10/3. And then over here, 1 cubed is 1, so I really have 1/3 minus 3, and that ends up to be negative 8/3. And because I had that minus between them, I have that minus here. These will be two negatives making a positive. So I have negative 10/3 plus 8/3, which ends up to be negative 2/3. And so I end up with that negative 2/3 as the answer for the exact area here. Okay, and some of you are like, well, how can you have negative area? And that is something that we will talk about in a future lesson. Let's just take it one step at a time and work on the math part today. Okay, moving on to example 2. This is one that you want to make sure that you view the problem as a power. So that square root we're going to look at as a 1/2 power. And then I'm going to take the antiderivative, which is again a power rule. So I'm going to add 1 to the power and then to flip and multiply, so divide by that in front. And I should get 2x to the 3/2. Because adding 1 to 1/2 becomes 3/2. If I flip and multiply with this 3, those are going to cancel. I'm going to have 2. Again, I put that straight line and the numbers a and b again, 1 and 4 in this case, to show that I'm evaluating using those numbers. This one doesn't have a plus or a minus, so I don't have to put it in parentheses. You can if you want to, just to always be doing the same thing. That's up to you. But the first thing I'm going to do is plug in 4. So 2 times 4 to the 3/2. and then I'm going to subtract and then plug in 1. So 2 times 1 to the 3 halves. And you have to remember what it means to be to the 3 halves. That's taking the square root and then cubing it. So the square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. And then over here, 1 to any power is 1, so this is a little easier. So just subtract 2. And so my overall answer in this case is 14. All right, let's move to example 3. And we're going to pull some trig in. So first of all, you have to ask yourself, is this a rule I know? Is it a trig identity? Is it a U sub? Something like that? Well, this is just a straight rule. So the tangent has a derivative of secant squared. So the antiderivative of secant squared is tangent. So tangent x is my antiderivative. I'm evaluating from 0 to pi over 4. And again, I don't have pluses or minuses, so I don't have to put those big parentheses. I can just say the tangent of pi over 4 minus the tangent of 0. And this is where knowing that unit circle comes in, and that's why I've pounded it into you in pre-calc. So the tangent of pi over 4 is 1. The tangent of 0 is 0. 1 minus 0 is 1. Now, if you don't know your unit circle and those numbers don't come that easily to you, then you need to go back and spend some time on that. Okay. Example 4 may be one that you try yourself because you may be to that point. So if you are, hit pause. Okay, and so you either hit pause or you're continuing to listen. So I am just having a bunch of power rules here. So adding 1 to the power and dividing by that number in front to get my antiderivative. So I have 2/3 x cubed minus 3 halves x squared plus 2x. Evaluating from 0 to 2. Okay, now this has bunches of pluses and minuses, and I need a little bit more room, so I'm going to come back over here and put my equals mark. But I'm going to put that big parentheses or a bracket or something like that around there because I have a lot to make sure I get the signs right. So I'm going to plug in 2, subtract, plug in 0. So 2/3 times 2 cubed minus 3 halves times 2 squared plus 2 times 2. And now I've plugged in 2, so I'm going to close that out, subtract, plug in 0. Now, a lot of times you're going to notice sometimes when you plug in 0, everything is going to go away. So you can go ahead and skip and write 0 down here if you want. But again, what's really happening is you're plugging 0 in. So 2/3 times 0 cubed minus 3 halves times 0 squared plus 2 times 0. And so, again, that whole piece is going to end up to be 0. Over here is where the real work is. 2 cubed is 8. And I have to multiply that by 2/3. 2 squared is 4. I have to multiply it by 3 halves. And then 2 times 2 is 4. When I do all that, I get 10/3. And then 10/3 minus 0 is obviously just 10/3. If you're bad at fractions, this may be something you need to practice and do step by step and show a little more work on. Now, example 5, you look at it and you're thinking, oh, this must be U sub, but it's really not. Since the bottom doesn't have a plus or minus, you can actually separate that and have x over the square root of x minus 2 over the square root of x. And after I do that scratch work, I can subtract these powers. This is 1/2 power, so 1 minus 1/2 would be a 1/2. So this whole fraction becomes just x to the 1/2. And then I can write this one as minus 2x to the negative 1/2. And therefore, I just have to do power rules, and I don't have to do anything crazy. In fact, if you tried to do a U sub, you would get stuck. So let me erase my scratch work here. And I'm going to take my antiderivative using my power rule. So I'm going to add 1 to the power and divide in front. So I'm going to get 2/3 x to the 3 halves. And then minus 4x to the 1/2. And I'm evaluating that from 1 to 16. So again, I'm going to come over here and give myself a little bit more room. Because this has a minus, I'm going to put a big parentheses and do my 2/3 times 16 to the 3/2 minus 4 times 16 to the 1/2. Then subtract the 2/3 times 1 to the 3/2 minus 4 times 1 to the 1/2. And so this first one, again, remember that this 3/2 power means the square root of 16 cubed. So the square root of 16 is 4, 4 cubed times 2/3. Then we're going to subtract 4 times the square root of 16, which is 4. So 4 times 4 will be 16. So when you do all those computations, you get 80/3. And I do recommend keeping things in fractions because once you start rounding off, you get error. And if you get more than, you have to have 3 decimal places correct on your AP exam. So fractions really are the best route to go, especially working something like this out. Then over here, again, 1 to any power is 1. So really this is 2/3 minus 4. So you have to get a common denominator. You have to subtract. You end up with negative 10/3. You may want to stop and practice getting those two numbers the way that I did. It's really good to know those things. Again, 2 negatives make a positive, and I end up with 90/3, which is 30. So ended up pretty nice number. All right, now last example here, number 6, absolute value. We don't have a rule for that. So there's a reason this is on here. And sometimes it is easier just to do things geometrically and figure out the area using geometry formulas. So let's look at what this looks like. Okay, so if we graph this function, it's an absolute value, so it's a V-shape. It's been moved right 1. It has a vertical stretch of 2. So when I graph it, it's going to have a 0 at 1/2. At 0, if you plug 0 in, you get 1, so that's right here. And if you plug 2 in, you get 3, so that's right here. You can get that general shape in there. And again, we want to find this area under here. And this is not the prettiest thing, but we're finding that area, and you have basically 2 triangles, a small triangle and a big triangle. So instead of trying to come up with some algebraic formula and use this fundamental theorem, it is easier, since these are perfect triangles, just to come up with those triangle formulas and get the exact area. So the first one, area of a triangle is 1/2 base times height. Our base is 1/2, our height is 1. And then the big triangle, 1/2 base. Base in this case is 3/2, or 1.5, and then our height is 3. And so if we calculate that, you can get 5/2, or 2.5 if you're in decimal form. And that is the exact area because, again, those were perfectly triangular shapes. The fundamental theorem is something we're really going to use more on things where they're not obvious, perfect geometry type shapes. And so sometimes with lines or absolute value, those kinds of things, we can come up with them perfectly in an easier way. So look out for those. Keep those in mind. And it should be a big clue because we don't have a rule for absolute value going backwards at our point. So should help you out. And that concludes this lesson.